Welcome back to the Interview Prep Podcast. Today we're going deep on Kubernetes and container orchestration, one of the most heavily tested topics in system design and infrastructure interviews. Whether you're interviewing for a backend role, an ML platform role, or a DevOps position, you need to understand Kubernetes inside and out. Let's break it down. Let's start with the fundamentals. Why containers? Before containers, deploying software was painful. You had dependency conflicts, environment inconsistencies between development and production, and slow deployment cycles. Docker solved this by packaging an application with all its dependencies into a lightweight, portable container. A container is essentially an isolated process that shares the host OS kernel but has its own file system, network stack, and process space. But containers alone aren't enough. When you have hundreds or thousands of containers running across multiple machines, you need something to manage them. That's container orchestration. Kubernetes, or Kubernetes, is the industry standard for this. It was originally developed at Google based on their internal system called Borg, and it's now maintained by the Cloud Native Computing Foundation. Let's talk requirements for a Kubernetes deployment. You need to think about how many services you're running, what's your expected traffic and scaling needs, what's your availability requirement in terms of nines, do you need multi-region deployment, what's your team's operational expertise, and are you running stateful or stateless workloads? Now let's dive into the architecture. A Kubernetes cluster has two main components, the control plane and the worker nodes. The control plane is the brain of the cluster. It consists of several components. The API server is the front door to Kubernetes. Every kubectl command, every internal component communication goes through the API server. It's a RESTful API that validates and processes requests. The EC database is a distributed key-value store that holds all cluster state. Every pod, service, and configuration is stored here. It uses the Raft consensus algorithm for consistency. If EC goes down, your cluster is effectively blind. The scheduler watches for newly created pods that have no assigned node and selects a node for them to run on. It considers resource requirements, affinity rules, taints and tolerations, and data locality. The controller manager runs a set of controllers, each responsible for a specific aspect of cluster state. The replica set controller ensures the right number of pod replicas are running. The deployment controller manages rolling updates. The node controller monitors node health. Worker nodes are where your actual application containers run. Each node runs a kubelet, which is an agent that receives pod specification from the API server and ensures the containers are running and healthy. The Kuba proxy handles network routing, maintaining network rules that allow communication to pods from inside or outside the cluster. And the container runtime, typically containered, actually runs the containers. Let's get into the key abstractions. A pod is the smallest deployable unit in Kubernetes. It's one or more containers that share network and storage. In practice, most pods run a single application container, but sidecar patterns are common where you add a logging agent or proxy container alongside your main container. A deployment declares the desired state for your pods. You specify how many replicas you want, what container image to use, and how to update. Kubernetes then works to maintain that state. If a pod dies, the deployment controller creates a new one. A deployment manages a replica set, which in turn manages the pods. A service provides a stable network endpoint for a set of pods. Since pods are ephemeral and get new IP addresses when recreated, you can't rely on pod IPs. A service gives you a stable cluster IP and DNS name. There are several types. Cluster IP for internal traffic only, node port to expose on each node's IP, load balancer to provision a cloud load balancer, an external name for DNS aliasing. An ingress manages external HTTP traffic routing to services. It's like a smart reverse proxy that can do path-based and host-based routing, TLS termination, and load balancing. Ingress controllers like Nginx Ingress Controller or Traefik implement the actual routing logic. Now let's go deeper on some critical topics for interviews. Scaling in Kubernetes happens at multiple levels. Horizontal pod autoscaler or HPA automatically adjusts the number of pod replicas based on CPU utilization, memory usage, or custom metrics. For example, you might set a target of 70% CPU utilization, and HPA will add or remove pods to maintain that target. Vertical pod autoscaler or VPA adjusts the resource requests and limits for containers. And cluster autoscaler adds or removes nodes from the cluster based on pending pods that can't be scheduled. For For custom metric scaling, you might use CADA, the Kubernetes Event-Driven Autoscaler. It can scale based on Kafka queue depth, HTTP request rate, Prometheus metrics, or any custom source. This is particularly useful for ML workloads where you want to scale GPU nodes based on inference queue length. Let's talk about storage. Kubernetes handles storage through the persistent volume subsystem. A persistent volume, or PV, is a piece of storage provisioned by an administrator or dynamically provisioned. A persistent volume claim, or PVC, is a request for storage by pod. Storage classes define different tiers of storage like SSD versus HDD and enable dynamic provisioning. For stateful applications like databases, stateful sets provide stable network identities and persistent storage for each pod, with ordered deployment and scaling. Networking in Kubernetes follows a flat network model where every pod can communicate with every other pod without NAT. This is implemented by Container Network Interface or CNI plugins like Calico, Cilium, or Flannel. Network policies act as firewalls for pod-to-pod traffic, allowing you to restrict which pods can communicate with each other. Service mesh solutions like Istio or Linkerd add advanced networking features like mutual TLS, traffic management, circuit breaking, and observability at the network level. Let's cover deployment strategies, which come up frequently in interviews. Rolling updates are the default strategy. Kubernetes gradually replaces old pods with new ones, ensuring availability throughout. You control the pace with max surge, how many extra pods to create, and max unavailable, how many pods can be down during the update. Blue-green deployment runs two identical environments. You deploy the new version to the green environment, test it, and switch traffic all at once. In Kubernetes, this is typically done by updating a service selector to point to the new deployment. Canary deployment routes a small percentage of traffic to the new version and gradually increases it. This is often implemented with Istio's traffic splitting or with multiple deployments and weighted services. Argo Rollouts is a popular Kubernetes controller that provides advanced deployment strategies, including Canary with automated analysis. Now for some advanced topics. Resource management is critical. Every container should have resource requests, the minimum guaranteed resources and limits, the maximum allowed resources. If a container exceeds its memory limit, it gets killed and restarted. If it exceeds CPU limits, it gets throttled. Proper resource configuration prevents noisy neighbor problems and ensures efficient cluster utilization. Use tools like Goldilocks or KubeCost to right-size your resource requests. Health checks in Kubernetes come in 3 flavors. Liveness probes check if the container is alive. If it fails, Kubernetes restarts the container. Readiness probes check if the container is ready to serve traffic. If it fails, the pod is removed from service endpoints. Startup probes are for slow-starting containers, giving them time to initialize before liveness checks kick in. Security is a major interview topic. Pod security standards define 3 levels: privileged, baseline, and restricted. Use RBAC or role-based access control to control who can do what in the cluster. Use secrets for sensitive configuration, preferably backed by an external secrets manager like HashiCorp Vault or AWS Secrets Manager. Network policies restrict pod communication, and image scanning tools like Trivy or SNYK check for vulnerabilities in container images. Observability in Kubernetes requires a comprehensive stack. For metrics, Prometheus scrapes metrics from pods and nodes, and Grafana visualizes them. For logging, the EFK stack with Elasticsearch, Fluent, and Kibana, or the Loki stack with Promtail and Grafana are standard. For distributed tracing, Jaeger or Zipkin with OpenTelemetry instrumentation help you trace requests across microservices. These 3 pillars, metrics, logs, and traces, give you full visibility into cluster behavior. Let's touch on Kubernetes in the context of ML workloads, since many interviews will ask about this. GPU scheduling requires the NVIDIA Device plugin, which advertises GPU resources to the Kubernetes scheduler. You request GPUs in your pod spec, just like CPU and memory. Kubeflow is the ML toolkit for Kubernetes, providing components for training, serving, and pipeline orchestration. And as mentioned in our ML serving episode, Triton Inference Server runs beautifully on Kubernetes with GPU support and auto-scaling. Here's your whiteboard summary. Draw a Kubernetes cluster with the control plane at the top containing the API server, ECT, scheduler, and controller manager. Below, draw 3 worker nodes, each containing a kubelet and several pods. Show a service object with a stable IP routing to pods across nodes. Add an ingress controller routing external traffic to services. On the side, draw the HPA watching pod metrics and adjusting replica counts. Show a persistent volume connected to a stateful set pod. Label the networking with a CNI plugin, and add a monitoring stack with Prometheus and Grafana watching everything. Let's close with key interview phrases. Say the Kubernetes control plane uses ECT as its source of truth, with the API server mediating all cluster state changes. Use horizontal pod autoscaler combined with cluster autoscaler provides two-level scaling, pod level and node level. Mention network policies implement zero trust networking by defaulting to deny all and explicitly allowing required communication paths. Talk about rolling updates with proper readiness probes, ensure zero downtime deployments. Say resource requests and limits prevent noisy neighbor problems and enable the scheduler to make optimal placement decisions. And emphasize the 3 pillars of observability, metrics, logs, and traces are essential for operating Kubernetes at scale. That's episode 5. Kubernetes is a massive topic, and we've covered the most interview-relevant parts. The key is to show you understand both the architecture and the operational considerations. Next time, we're diving into microservices architecture. See you then.